Okay, I'm back today and I'm going to try to develop a unifying theme for several complex aspects of atomic structure, orbital hybridization, VSEPR, angles and shapes. And I'll take it slowly. So I'm going to start with the simplest orbital hybridization. The example of the molecule is going to be beryllium chloride, BeCl2. Beryllium is an alkaline earth metal, so it has two valence electrons. They both start out in the s orbital, but if beryllium is going to bond with two things, the two electrons are going to try to get as far apart from each other as possible. So they form an sp hybrid orbital. And when we bond the two chlorine atoms to the beryllium central atom, we have AX2 notation, no unshared pairs of electrons. The shape of the molecule is linear, and the angle formed between the two bonded atoms is 180 degrees. The level of complexity is sp2. This would be an atom that has three valence electrons. Best example of that would be boron. That has three valence electrons. It's a metalloid. I used it yesterday in a video. We're going to have it bond to three fluorine atoms, covalently bond. And the AXE notation will be A for boron, X3 for the three fluorines, and no E because there is no unshared pair of electrons around the central atom boron. For these three bonding orbitals to get as far apart from each other as possible, they are going to form 120-degree angles. The molecule itself will be trigonal, meaning triangular, but planar. It's not a three-dimensional molecule, it's two dimensions. Along the same lines, there is a rather complex molecule, sulfur dioxide, whose Lewis structure I'll get into in a different video. But for now, sulfur dioxide will double bond with oxygen, single bond with a second oxygen, have an unshared pair of electrons around the sulfur. So the A for sulfur, X2 for the two oxygens, and E for the lone unshared pair of electrons. So again, we have three bonding sites, the two oxygen atoms that are bonded and the unshared pair of electrons that has the potential to bond. They'll rearrange themselves as far apart from each other as possible, but the angle will be slightly less than 120 degrees because the unshared pair of electrons will be pushing down on the bonding electrons and make it into or V-shaped molecule. Then we move up the sort of hierarchy into sp3 hybridization. This will be compounds which has the potential to form four bonding sites. So we'll start with carbon and four hydrogens. We did this yesterday. It's methane. AXE notation is AX4, no E's. The angle is 109.5 degrees, and it's a tetrahedron. Moving to a slightly different molecule, ammonia. Nitrogen has an unshared pair of electrons, three hydrogen atoms bonded to it, so AX3E. It's still sp3 hybridization because nitrogen has four potential bonding sites, so there are four potential bonds, 3 hybridization. Because this unshared pair of electrons is pushing down on the bonding sites, this does not form a tetrahedron, it forms a trigonal pyramid, a three-dimensional structure. The angle is about 107 degrees. The final molecule I'll use for this video is water. So oxygen is the central atom. It has two unshared pairs of electrons plus two single bonds to hydrogen. Its AXE notation is AX2E2. This is still sp3 hybridization. In theory, our basic structural, oh shoot. Okay, my disk is getting full. It starts off as a tetrahedron, but it has two unshared pairs of electrons, or V-shaped. And its angle is about 104.5 degrees. Not the 109.5, but the full tetrahedron. The two unshared pairs of electrons push down on the actual bonds between hydrogen and oxygen and force it into a slightly closer proximity to each other than the full tetrahedron. That's it for this part of the video.